Hello, hello, hello. Welcome back. It is Saturday, I believe, the 23rd of May. Can confirm? Yeah, Saturday. Sorry, I normally have my calendar open. I should always check this before I start, and I just never do. Hope you guys are enjoying it. This is where it's getting like really, really hot, and I imagine I would be so surprised if people are like inside coming to watch a math paper. But in case you are, today is OCR MEI, the comprehension paper. So I was looking at that and thinking, like, that looks really, really interesting. I've not seen anything like this. A lot of people wanted me to cover the OCRB, and so I'm just kind of curious to see what's under that. And then after I'm done, I will go out and enjoy the sunshine and make sure I make the most of this like 28, 29-degree weather before the hell week of half term and exam season begins. So without further ado, I don't think I should do anything other than just sort of get into it. So I've got my papers. I've got the insert for whatever that's going to be required for. I've got my answer booklet. I say we just get into it. So I'll share the entire screen so that you can get both at once. Theoretically, we have 2 hours. I think I'm going to give myself leeway on time. I think I'm going to go through, get a sense of what the paper's like, give myself time to check it properly, and kind of, demonstrate all the good exam technique you guys would need in order to do well in this. Actually, before we start, I will discuss this. So because I don't know what's about to happen, because this is going to be a complete pure blind solve, and it's called pure maths and comprehension, it seems like it might be a little bit deeper. There may come moments where I really don't know what I'm doing based on like exam technique. And so I think what'll be instructive in those moments is how I get around the problem and try and demonstrate like good exam technique to try and get out every mark I possibly can. So I'm really, really, really curious to see how this turns out. So let's get into it. Alrighty then. So well, first let me go to here. Let me zoom in. So this will be question 1. Now let me look at question 1. So section A, as usual, looks like it's going to be not too bad for the OCR. So coming into here, if we have x over 5 is bigger than 6 minus x, we simply move the x across and make it 6x over 5 bigger than 6, divide by 6, and x is bigger than 5. Okay. Question 2, the function is defined as that. Find an expression for the inverse. Well, we're going to say if y is equal to the root of 1 plus 2x, we simply swap around the x and the y and then make y the subject of the formula. So x squared minus 1 over 2 is equal to y, and therefore that is the inverse. And the domain of the inverse is the same as the range of the original. And given the domain of the original starts at x equals minus a half, it gets bigger. If we plug in that limit of x equals minus a half, that would make that part 0, which would make that 1. No, lies. It would not make that 0. That x equals 0 would make that 0. X equals minus a half makes that minus 1. So the range, excuse me, of the original is that y is bigger than 0 or equal to 0, which means that the domain of the inverse is also bigger than or equal to 0. Explain why x squared plus 1 with all real numbers has no inverse function. That would be because if the domain is all real numbers, that means it is a many-to-one function. And the problem with being a many-to-one function is in order to have an inverse, you have to be a one-to-one function. So if I write that down, that will hopefully suffice. So if we were going to try and make that inverse there, we would need to restrict the domain to at least, and you can find that. So in this case, by finding, just sort of answering the question they could have asked, this minimum point here is at 0, 1, which means that in order to have an inverse, we would need a domain that's limited to at least all the positive numbers or all the negative numbers. But we can't have any domain that sort of that straddles this turning point, because then we would, again, get multiple y values. Sorry, the same y value out for multiple x values, which would cause an issue. Here, question 3. Shows a curve of y equals x to the 5, and the square. The curve cuts into 2 parts. Area to the left versus area below. Okay, well, why don't I find the area below? So the area of the square is simply 1. And then the area below is going to be the integral from 0 to 1 of x to the 5, which is going to be a 6x to the 6 between 0 and 1, which is just going to be a 6 minus 0 equals a 6. So that means to the left must be the total of 1 minus the below area of a 6. So that's 5, 6. And then clearly then left over below is 5, 6 over 1, 6 equals 5. Great. In this question 4, we've got rationalizing denominator. So in the first one, 1 over root 2 plus 1, we're going to multiply top and bottom. It's always blindly, whatever the thing was, with the sign changed. So I'll do these just for the space and like the presentation. I'm going to do these individually and then bring them together. Sorry, that's not root 2 on the bottom. So difference of 2 squares there makes that 2 minus 1, which is just root 2 minus 1. The second term will multiply by root 3 minus root 2 on top and bottom. And you get root 3 minus root 2 on the top and 3 minus 2 on the bottom, which is just root 3 minus root 2. And then the third set, 1 over 2 plus root 3. Apologies, don't make a transcription error now. That is a 2. I'm thinking we got to do 2 minus root 3. So it's 2 minus root 3 on the top, and on the bottom it's 4 minus 3, which again is just 1. So when we bring these all together, it's root 2 minus 1 plus root 3 minus 2 plus 2 minus root 3. These roots cancel. That's meant to be a root, so that cancels with that, and you end up getting 1. And then question 5, use a substitution. Find the find the value of the positive integer c such that this integral is that thing. Okay, so whenever I'm doing a substitution, very first thing I will always do is limits. So when x equals c, u equals c plus 1. When x equals c plus 4, u equals c plus 5. Okay, so I've done my limits. Now I'll do my dx. I'll say that du dx is equal to 1. So I'll say that du is equal to dx. Okay, then substituting that in for dx, that will just become du. Now I have to do the body of the thing. And I'll say that x is equal to u minus 1. And then putting this all together, the c limit becomes c plus 1 in u. The c plus 4 limit becomes c plus 5 in u. The x becomes u minus 1. X plus 1 is u, and that's all squared. And dx is equal to du. So I've now transformed it into this new simpler integral. And this is basic polynomial integration in that I can separate out the fraction and call this 1 over u minus 1 over u squared. And let me just rewrite that one more time, because 1 over u is nice and integrable, but I want to call this u to the minus 2, so that I can call that ln u and then raise the power to minus 1, divide by that to turn it positive, and that is between c plus 5 and c plus 1. Well, yeah. So ln of c plus 5 plus 1 over c plus 5 minus ln of c plus 1 minus 1 over c plus 1 is going to equal ln 3 minus a third. So in this case, ln of c plus 5 over c plus 1 plus 1 over c plus 5 minus 1 over c plus 1 is ln 3 minus a third. I'm not sure we know for certain that c plus 5 over c plus 1 is equal to 3, because it might... No, I suppose it does, doesn't it? I'm going to try it just in case it falls out. So if c plus... Because that I don't want to have to be dealing with the algebraic fraction of it all. Let's just start by saying this. That this thing must be equal to 3, kind of like a sort of comparing parts. That would mean that c plus 5 is 3c plus 3. So 2 is equal to 2c, so c equals 1. Is 1/6 minus a half? I'm just going to plug that back in and just confirm on the left-hand side. So ln of 6 over 2 plus 1 over 6 minus a half is ln 3. Yeah, ln 3 minus a third. So that does work. So c equals 1. And then question 6. Show detailed reasoning, solve. Okay, so what I see here, first of all, I'm seeing an angle range. And I was looking, but no, this is, so it's not something like 2x or 3x or something where I have to transform this into, it's just an x, so I get to just use between 0 and 360. So that means that tan x minus 3 over tan x equals 2. And then multiplying by tan x everywhere, we're going to be able to form a quadratic equation in tan x. And when I solve for that, I'll get tan x minus 3 tan x plus 1 equaling 0. So tan x is equal to 3, or tan x is equal to minus 1. So then I'll just run that on my calculator. I don't think... Well, let me first make sure my calculator is set to degrees. Whenever there's trig, you should be suspicious, right? Always check. So inverse tan of 3 gives me 71 point... Now, does it want it in a particular... Nope. So I'll just give it to one decimal place, 71.6. Or I can add 180 to that and get 251.6 for that. And then for this one, x is equal to... Now I have a feeling this is just minus 45. And indeed it is, but that is not in the range of 0 to 360. So I will add 180 and get 135. You can't see this. Add 180 again, we'll get 315. So those are your 4 values of x. Okay, 7. Okay, what I'm going to do, I see a 4 theta, and these are 8 thetas. So I can use my double angle formulas to immediately write these in terms of 4 theta. So sine of 8 theta will be 2 sine of 4 theta cos of 4 theta, and that all times tan of 4 theta. Now I'm sort of projecting ahead and seeing that the causes there will cancel, so I'll have sines. So I'll do the double angle formula in cos in terms of the sines as well. Now, cos of 2 theta is 1 minus 2 sine squared of the old argument divided by 2. Okay, so this will be 2 sine of 4 theta cos of 4 theta times sine of 4 theta. Oh, yeah, this will be fine. Over cos of 4 theta plus 1 minus 2 sine squared of 4 theta. The cos 4 thetas will cancel, so you get 2 sine squared 4 theta plus 1 minus 2 sine squared of 4 theta, where these will obviously cancel, and you'll be left with 1. I love this. I call this harmonic form. So we're going to write it in the form of, for question 8a, we're writing this in the form of r sine of x plus alpha. Now, using my addition formula, I know that that is r sine x cos alpha plus r cos x sine alpha. And just while we're here, I'll point out that you do have a formula book kind of here at the top, which should give everything you need. So you can use these trig identities to get the addition angle formula that I'm using now, as well as the double angle formula if you forget them. So dipping back here into question 8. Right, so we'll compare that with the form that we have. And we'll say that r sine alpha on this cos x bit is just equal to 1, because the coefficient of cos x is just 1. And r cos alpha is root 3, which is just the coefficient of the sine x. Then I can say that dividing through, we say that tan alpha is 1 over root 3, which I, again, really should know off the top of my head, but screw it. So that would be 30. Let me just check. They wanted it in degrees. No, they wanted it in radians. Apologies. So let me convert that to radians, and instead it should have. What exam technique was that? That is the second you think you're done with the question, reread it to make sure you've actually answered it. It's so easy to quote something in a way that they don't want. So the alpha is in radians, which I have not found. And the way you find r is by saying that r squared is 1 squared plus root 3 squared, which is obviously 1 plus 3, which is 4, so r equals 2. So in other words, it is 2 sine of x plus pi over 6. So hence solve this thing. Well, when it says hence, it means we have to get this form here and then substitute in the new form. So if I expand this out, cos x equals root 3 minus root 3 sine x, then by moving this over, I get cos x plus root 3 sine x is equal to root 3. From there, we can use the expression I just found to say that that is equal to 2 sine of x plus pi over 6 equals root 3. We can, whenever we're doing this, we always have to get it into the form of trig equals value. So in this case, the trig equals root 3 over 2. And in radians, again, do I know this? Yes. Did I sleep well enough? No. So we're just going to use the calculator. There's no point risking an execution error if I don't need to. So it's pi over 3. Now I also know from the cast diagram, this is the point immediately after doing inverse sine that I need to use the cast diagram to find all my values. So we want A and we want S. I used cast diagrams as opposed to graphs. Apologies if you prefer graphs. The method's still the same, where in order to find the other region in which sine is positive, we need to do pi minus that thing. So it's 2 pi over 3. I want to check my interval here. No, I shouldn't have done that. No, I should have done that because that's still less than pi. So that's minus pi going round to pi. I have found all of those. Let's now subtract pi over 6 from both sides, and I'll get pi over 6. And then that's 4 pi over 6 becomes 3 pi over 6 becomes pi over 2. Brilliant. Okay, so that is not the whole of section A. Okay, so let me give myself some more room here. This question is about this thing. F of function is some random nonsense. Okay, let me just sort of zoom out. I need to see what's happening here. So apologies if this is small on your screen, but we're told that f of x is x to the 4 minus x minus 1 over 3x minus 2. And we want to show that there is a root between 1 and 2. All we would do is, in fact, now I will bring the calculator across. Not because this is particularly complicated, but because otherwise it'll just be really boring you watching me type it in. Now, also, I'll just show you. So you can tell I was doing some stats earlier today. Let's go back to calculation. Whenever I'm substituting, I'll just type in the thing I want to substitute equals, and then use the answer button in order to substitute. So answer to the 4 minus answer minus 1 over 3 answer minus 2 is minus 1. And f of 2 is equal to, and again, I'll do 2 equals, and then answer to the 4 minus answer minus 1 over 3 answer minus 2 is 55 over 4. So what we can say is that there's a change of sign in the interval. So change of sign in the interval and continuous in interval. Therefore, root in interval. Okay. Apologies for my handwriting. So now we have a spreadsheet being used to find a root of the equation. Write down a suitable number to use as the next x value in the spreadsheet. So what they seem to be doing... Hello. How's it going, Vivan? So we know there's a root between 1 and 2. We've proven that much. What are they doing? So it seems like they're quartering it. I'm wondering if they mean just anywhere between 1.125 and 1.25, or if they want it to be more systematic than that. Oh, year 12 mocks next week. Good luck with those. AQA Physics Paper 3. I will definitely have advice for those questions. If it's okay with you, I'm going to leave that to the end just so that we can keep the live solve good. Or maybe I'll do it out when I'm finished with section A and then timestamp it. But just give me a few more minutes and then I'll answer that question specifically. In the meantime, I just want to find a suitable value. So this would be anywhere between the two. So I might 1.15 maybe? It just says a suitable number, not the suitable number. So I'll just say it should really, we know that, okay, there's this change of sign in that interval. So the root is somewhere in that interval. So I'll maybe say it's either 1.15. They might accept 1.20 might be good as well, just to sort of shave it off that top end. I suppose 1.135 would be interesting because then you could prove it's 1.12 down to 2 sig figs. But yeah, I think this should be where we'll see in the mark scheme. This is a bit of a weird question. So determine a root of the equation, give your answer correct to 1 decimal place. Huh. Why is this only 1 mark? Oh, wait, it's got to be correct to 1 decimal place. So all I'm going to try is, yeah, I'm going to actually put this in. I'm going to put in 1.15. So 1.15 equals, now also I'll write that I'm doing that. So f of 1.15 is, now this thing is answer to the 4 minus answer minus 1 over 3 answer minus 2. Yeah, that's negative 0.0906. So therefore, a change of sign in the interval of 1.15 to 1.25. So therefore, it must be 1.2 to 1 decimal place. Okay. So D thou. This feels not very section A. Am I out of section A yet? Or am I just going crazy? No. Where does section B start? Damn. All right. This paper's going off. All right. So, figure D explained why it looks from rows 2 and 3 of the spreadsheet as if there is a root between 0 and 1 because there's a change of sign interval. But it wouldn't necessarily work if there was a continuity issue. Explain why this process will not find a root between 0 and 1 because there's a vertical asymptote instead. Discontinuous. Okay. So then here we have in question 10 this weird quartic looking thing. Okay, so now we need to sketch the gradient function. And we seem to need to do that on top of the thing itself. I thought they would have given me a clean graph. All right, guess not. So what we know is that wherever we have turning points, the gradient is 0. In this region, the gradient is positive. In this region, the gradient is negative. And then it's positive, and this is negative. So that's what I think. It kind of has that cubic shape. Now, we have this other thing happening. So in question 11, shows the curve with equation y equals g of x, where we're given what g of x is, and the curve of the gradient function, which we can see is the dotted line, show that the x coordinates of the points on the curve where the gradient is 1 satisfy that equation. Okay, so we're told that g of x is x sine x plus cos x. So if we differentiate this, we get first d second plus second d first. And then this guy integrates to minus sine. So this whole thing will just become x cos x. Okay, so we're also told that the gradient is 1. If we divide both sides by x, we get this. And if we subtract cos from both sides, we get this. Good. Use the Newton-Raphson method with a suitable starting value to find the smallest positive x coordinate of a point on the curve where the gradient is 1. So this curve we are now looking at in question 9 is the equation we need to solve for where their gradient is 1. So we're looking for this point around 5. Because that is, I think, the smallest x coordinate where this equation is satisfied. So the starting value will be 1. Will be 5. And then the Newton-Raphson formula, which is given on your formula sheet, is the Newton-Raphson, which should be given on your formula sheet. Oh, there it is. There it is. So we know that x plus 1. I'll just write out the formula so I never lose what I'm doing. Now, coming back to this guy, if f of xn is equal to 1 over xn minus cos xn on this graph, we need to find the gradient function on this graph, which would be minus 1 over xn squared plus sine of xn. The solution correct to 4 decimal places. Right, and so in other words, what I'm going to type in, I'm going to start with x1 equals 5. So 5 equals. I'm then going to say answer minus the f of x is equal to 1 over x minus cos of x. And that's all going to be over minus 1 over answer squared plus sine answer. So if x1 equals 5, oh, I don't think I did this right because I have it in degrees. Bother. Every time I am supposed to check. When will I learn that I need to check? All right, so let's try that again. So that should be in radians. Thank you very much. Once more with feeling. So answer minus 1 over answer minus cos answer all over minus 1 over answer squared plus sine answer. So that will be 4.916, 4.917, yeah, 4.917. So it's 4.917 to 3 decimal to 4 decimal places. No, guys. All right. Yeah. Fine, I'll do it again just because like they wanted it a certain way and I didn't give it to them a certain way. Apologies, but it's like, is it annoying? Yes. I find it annoying, you find it annoying, but like it's what they want. You got to give them what they want, even if what they want is silly. So over minus 1 all over answer squared. You see, this is why I'm doing it on the screen. So at least you can track what I'm doing. 6, 2. Yeah. Okay. All right. So that's the answer corrected for DP. And maybe if they ask for the iteration, maybe I'll write it explicitly. So I'll say n plus 1 is equal to, I'll write if it went in my calculator, I'll put exactly what I put in the calculator on paper so they know what I was doing because they can't see what I just did. Okay, so that was my iteration, which I wrote out. Okay, cool. So I know I've got the right answer. Explain why x1 equals 3 is not a suitable starting value because it lies close to a turning point. And the problem with lying close to a turning point with Newton-Raphson is you're dividing by this gradient function, and the value of the gradient will be close to 0 at x equals 3, which means you'll get close to a divide by 0 error, and you're just going to get shooting off to infinity. So bad. So f dash of 3 is close to 0, which causes a problem dividing by 0. Alrighty then. I really thought section A was going to be shorter, but I do promise I am going to get to your physics paper 12. Oh, no, this is the final question. Okay, and then I'll answer it. So we have this parametric equation. Determine the exact coordinates of all the stationary points. I am going to assume that by stationary points, they mean that dy dx is equal to 0. Now, dy d theta is minus 2 sine theta minus 2 sine 2 theta, using the ax plus b rule for differentiating that trig. I know that dx d theta is given by 2 cos 2 theta. And therefore, I know that dividing these through, that dy dx is equal to dy d theta over dx d theta. And that will equal 0 at the turning points. Or in other words, dy d theta is equal to 0 at the turning points. Dividing both sides by minus 2, just to make it more pleasant to deal with. Using my double angle formula to split this out. And then we get sine theta into 1 plus 2 cos theta is equal to 0. So we have two possibilities. Either sine theta equals 0, which in this interval means theta can equal to 0, which doesn't look right. If theta equals 0, x equals 2, y equals 3. No, that does work. Okay, so theta equals 0 or theta equals pi, but not 2 pi because 2 pi is not in the interval. Or we can have 1 plus 2 cos theta equals 0, which means that 2 cos theta is minus 1. Cos theta is minus a half. Oop, no sign errors today. And again, tired brain makes silly mistakes, so I'm not going to risk it. And that is giving me 2 pi over 3. And because cos is negative, I know I'm looking in the sine and the tan region. I know that it was also going to be 4 pi over 3. Or it's going to be 2 pi minus this answer I found, which is again 4 pi over 3. So I found my 4 theta values, but now I need to plug those back in order to find the exact coordinates. That's why this is 8 marks. Okay, so when theta equals 0, so the reminding myself that the exact coordinates are cast diagram. Yeah, I love a cast diagram. I hate drawing out the diagrams. Cast diagrams are the way to go. Trust me. So it's going to be sine 2 theta plus 2, 2 cos theta plus cos of 2 theta. All right, so let's plug in. When theta equals 0, I'm going to get 2, 3. When theta equals pi, I'm going to get sine of 2 pi is 0, so that will also be 2. So that's going to be this guy. It's going to be 2, and then that will be minus 2 plus 1. It's minus 1. Theta equals 2 pi over 3. That would be sine of 4 pi. In fact, I mean, true, but then you have to know how to draw the graphs, which is it's a problem for some people. I just find cast diagrams faster. It's also the way I was taught, and I think the first thing you're taught is the thing you gravitate to. Yeah. So there's really no preference. I mean, there's no major difference. Just like whatever you can do more consistently, do that. So plugging that in here, the x coordinate seems to be 4 minus root 3 over 2. In fact, no, this is sufficient work that I'll show you. So 2 pi over 3, sine of 2 answer plus 2 gives me that coordinate. Then 2 pi over 3 2 cos answer plus cos 2 answer. Well, I don't know why people are cast diagram snobs. Cast diagrams are just absolutely amazing. And 4 pi over 3. I suppose the only reason to not do cast diagrams is they aren't good for the special values of 0, 1, or -1, but like, they're just so good. And they're really good for people who don't deeply understand the math. Like whenever I'm teaching people who are doing math and then go, ooh, this is harder than I thought, cast diagrams are 100% more understandable to people, I find. So 4 pi over 3. So sine 2 answer plus 2. So it's 4 plus root 3 over 2. And again, 4 pi over 3. And then 2 cos answer plus cos 2 answer. Yes, the minus root 3 over, minus 3 over 2 again. So those are my coordinates. Write down the equation of the line with symmetry of the curve. That's going to be x equals 2 from the look of it. Yeah. Okay. Alrighty then. So that is the end of section A. Now, let me take a little bit of time because there was someone in the comments. There was something I wanted to talk about. Yeah, someone said, I was struggling with AQA Physics Paper 3. That's practical physics. Wanted to hear if you have any advice with those questions. One, know all your required practicals. What measurements you take, how you make them, and why. 2, I can give you the advice I give to a lot of people doing the practicals for IB, which is it's all about taking a formula and turning it into a straight line where you can interpret the gradient and intercept. The second point is to understand how to combine your uncertainties. And the third point is how to deal with error bars. Drawing max and min gradients. I'm not sure if error bars... No, I think they are in AQA Paper 3. Be really, really careful with the wording. Like, that's a paper where a lot of the marks are due to just exam technique. Just reading the questions and making absolutely certain you know what they're asking for their specific question. Because they can ask some... It's not just... It's annoying stuff. They can ask annoying stuff if you're not paying very close attention. So really read the questions well, parse out all the meaning. And I would say be very selective with the questions you do. So like make sure you do all the good questions first. And then if it seems like you have to do some nonsense trying to work some stuff out that's going to take some time, make sure that's happening at the end when you've sort of banked your safe marks. Okay, was there anything else I needed to discuss? Makes sense. Okay. All right, so I think it's section B time. I'm about to discover what section B is. So section A, not too bad, fairly standard stuff. This question, the questions in this section refer to the article in the insert. You should read the article before attempting the questions. All right, well, this is the insert. Let me pop that over here. Actually, no, let's read it first. So let me, let's find out what's happening here. So tangents and normals to a quadratic. We have a quadratic with tangents drawn at 2 points. And where those 2 tangents intersect. Oh, so they happen to intersect at the mean of the x coordinates of the 2 points we drew the tangents at. Yes, you do have 4 pieces of paper. You got your formula sheet, you have the insert, the question paper, and the answer booklet. It's one of the reasons I quite like Edexcel is because the questions and answers are at least together. Okay, so for the curve that, the equation of a tangent as a general point that is this. So the equation of the tangent at one point is that, good. There's a similar equation for the second point, good. And if we, what are they doing here? They're subtracting the 2 equations, it looks like. Or no, they're just rearranging this. Yeah. So we equate them. So the y's are equal at the point of intersection. They rearrange it, hence that. Okay. The general quadratic has that function. The tangents at any 2 points also cross at a point whose x-coordinate is equal to the mean of the x's of P and Q. So in other words, this first case was only for the specific case of y equals x squared, where they showed that the 2 tangents cross at the mean of the x-coordinates. That's interesting. Didn't know that. They're trying to generalize it now to all quadratics. So if you have the tangents taken at 2 x points, if you average the x's, that's where the 2 tangents will intersect. And we have this random equation for what the y-intercept will be, y-coordinate of that point of intersection will be. This is equivalent to some other nonsense. The first formula looks simpler, but the second one is in terms of the x-coordinate of the point of intersection. Apart from the last term. Right, okay. For pairs of points where the difference between them is h, the point of intersection of the tangent lies on this curve, correct? This curve is a translation of the original curve. That is correct. This is weird. Guys, this is a weird ass paper. I can understand why not a lot of schools want to do this. Training people for this must be weird. So we have this figure. I mean, we'll see where that goes. Shows, okay, we've gone back to y equals x squared. I'm commentating because I'm showing you what I'm making sense of as we move through this. So I haven't fully processed it, but I can refer back to it as required. So now we're taking normals at 2 points and where those intersect. Now this is funny because you would probably get really into this if you were doing further math and you were doing conic sections. I think a lot of this comes into play for that. So for this curve, the coordinates of the point of intersection of the normals at these 2 points are not as simply related to the coordinates of A and B. So they give us the normal in terms of t. So in terms of t1 and t2, so the normals cross at x coordinate and y coordinate given by the 2 parameters t, and that's all they tell us. Okay. So page 4 is redundant. So there's 3 pages of information. A lot of it has to do, in fact, there's only really 2 pages of content there. So they have to do with the tangents and normals of quadratics and where the tangents and normals at 2 points intersect. Cool. Okay. Substitute appropriate values. Okay, let's scroll back across now. Substitute appropriate values. Wait, does it tell us? Does it tell us the question? Because it's giving us the question. Oh, it now suddenly randomly does decide to give you the question here as well. So I actually no longer need the question paper. That's interesting. So it actually solves your problem of having all these sheets of paper on the desk. Because as soon as you move into section B, you can actually get rid of the question paper and just have the insert and the answer paper. So that's good to know. So I'm going to get rid of that. Let's just go to the insert. So for 13, substitute appropriate values of T1 and T2 to verify that this gives the correct value for the y-coordinate of the point at A and B in C1. Okay, so when it says appropriate values of T1 and T2, we need to work out the, so at A, we know it has points, coordinates -3, 9, and B we know has coordinates 1, 1. Okay, so here we know that the x coordinate so the general point is t and t squared. So here t is equal to -3, and here t is equal to 1. So t1, t2 is equal to -3 times 1, which equals -3, which is the y-coordinate of the point of intersection. So if the intersection is at -1, -3, then it does work. -3 equals -3. Good to go. So that does give the correct expression for the y-coordinate of the point of intersection. Cool. Edexcel is so much nicer. Okay, so 14. Substitute appropriate values of T1 and T2 to verify that that expression gives the correct value for the y-coordinate in C2. Well, this is C2. Where again, the general point has t and t squared, where again, A is, so we're going to take T1 is again equal to -3 and T2 is again equal to 1 because they've picked the same 2 points. And we're going to substitute it into, in fact, so it's T1 squared plus T2 squared plus T1, T2. You can see me going slower as I'm trying to piece together what's happening. Plus a half. So let's plug that in. So it's going to be -3 squared plus 1 squared plus -3 times 1 plus a half. So it's 9 plus 1 minus 3 plus a half. 6 plus 1 is 7. So it becomes 15 over 2. Which is 7.5. Does it say explicitly where they intersect? Which is 7.5. Okay, which is the y-coordinate of the point of intersection. Do I want to be super explicit here? Yeah, so the intersection, okay, I'll just do it as super explicitly. So it's at -12 and 7.5, so that does work. Show that for the general quadratic, which this is not. The equation of the tangent at the point with x-coordinate t is this. So looking at the insert, it doesn't lead us to there explicitly, so we have to work this out ourselves. Okay, so I'll just do as I'm told then. So what we know here is that dy dx is equal to 2ax plus b. And then at the point with x coordinate t, that would be 2at plus b. So we know the point would be at t, and then the y coordinate of that point would be at squared plus bt plus c. And then from the straight line equation, we know that y minus this y coordinate equals gradient times x minus the x coordinate. So that is my 2at plus b lots of x minus 2at squared minus bt. So y minus at squared minus bt minus c equals that stuff. And then rearranging it, you get minus at squared, the minus bt's cancel, plus c as required. Good. Hence show that for the curve with equation y, well, the general quadratic that we just did, the tangents at 2 points, P and Q. Okay, so show that show that they cross at the mean. Okay, so what we know is that the first normal, so from x equals t1, we know that the tangent is given by y equals 2at1 plus b lots of x minus at1 squared plus c. And we know for a second point where x equals 2, the tangent line is given by y equals 2at2 plus b lots of x minus at2 squared plus c. And then they intersect when the two y coordinates are equal. So that's when 2at1 plus b lots of x minus at1 squared plus c equals 2at2 plus b lots of x minus at2 squared plus c. The plus c's will cancel. We want to find that x is the average of t1 and t2. So I'm going to use a similar method to the one that they taught me for the general one, right? So they made me before set the two y's equal to each other and rearrange to make x the solution, right? So we need to make x the subject of the equation. To do that, we're going to get all the x's on one side, everything else to the other. So 2at1 plus b x minus 2at2 plus b lots of x equals at1 squared minus at2 squared. So in other words, 2at1 minus 2at2, and the b's will cancel, lots of x is equal to a into t1 squared minus t2 squared. So in other words, 2a into t1 minus t2 lots of x is equal to a into t1 minus t2 into t1 plus t2. The a's will cancel, the t minus 1's will cancel, so 2x is equal to t1 plus t2, and x is equal to t1 plus t2 over 2, which I think solves this. Okay. This is fun. I would very happily do a lot more of these papers. Show that the expression of this nonsense is equivalent to that other stuff, as given in lines 15, 16. Jesus, what are they doing? I can't believe this has been here the whole time and I've never done this. The y coordinate can be shown to be this thing. This is equivalent to that thing. All right, let's try to do that. So it's noticeably, it's going the other way, which I find interesting. Okay, let me expand this out and do a whole bunch of nonsense on it. So here, Or in fact, let me have a quick look at the questions and see how much of the insert I need. I'm not sure how much I'll need because I want to give myself some more room here, because I think this can kind of be done in situ. So here, if I expand it out, I get a, that looks like a 9, not off to a great start. So a over 4, because I just want to get rid of that. And then I'll square out the top and get xp squared plus 2xp xq plus xq squared. Second term is going to be completely unchanged. The plus c is completely unchanged. I'm going to make that a over 4. And again, this is going to be xp squared minus 2xp xq plus xq squared. Too long. Right. So that is going to be a over 4 into xp squared plus 2, because I can just tell I'm going to make a sign error, so I'm going to be really explicit about this. So it's this minus that. So it's minus xp squared plus 2xp xq minus xq squared. Cool. And then we add on the rest. That remains unchanged. So that becomes a over 4 into cancel, 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 4xp xq plus stuff. Which is, and then the 4's cancel, so it equals this as required. Okay, 17. Show that for this curve, the equation of the normal at this point is that. Okay, so we're going to find dy dx, which is 2x, and then when x is equal to t, dy dx is equal to 2t. So the perpendicular gradient is, well, I'll do that over here. So what that means is that the perpendicular gradient is going to be minus 1 over 2t. So that will be the gradient. We know the coordinates of the point it goes through. So y minus t squared equals that gradient into x minus t. And we want it in the form y equals. So let's just expand it out. So that's minus x over 2t plus, well, t over 2t. So therefore, y is equal to minus x over t. This I'll add the t squared across to the other side, and this gives me my plus a half as required. And then finally, so actually not a lot of this needed to be done with cross-referencing from the graphs, apart from getting the coordinates of the points of intersection to confirm. Like a lot of this was self-contained. A student is investigating the intersection points of tangents to the curve that. She uses software to draw tangents differing by 5. So that means h equals 5. This is one where I am going to go back. Because this is where this, as soon as I see this difference in x coordinates, that makes me think of this point here. Find the equation of the curve that all the intersection points lie on. So all the intersection points lie on the curve y equals ax squared plus bx plus c minus 25a over 4. But we're told in this case that a is equal to 6, b is equal to minus 7, and c is equal to 1 for this quadratic, because this was done for the general quadratic, which means that, put simply, y will be equal to 6x squared minus 7x plus 1 minus, well, 25 over 4 times 6. 25 divided by 4 times 6 is 37.5. So it's 6x squared minus 7x, well, plus 1 minus that is plus 38.5. And I think that is the answer to that. That was great fun, guys. I think that's the end. Yeah, end of the question paper. That was really good fun. I would happily do some more of those. That section B was top notch. I can see why all of you hate it, but I love that. All right, let me go through and check it and see how I would do that. Oh my God, did I get that paper done in an hour? All right. This is just, yeah, maybe OCRB just works for how my brain works, I suppose. All right, let me check and give some commentary. Cool. That genuinely took me by surprise. Solve this inequality. I mean, that's not too bad. Let me just confirm it for like a number very close to 5, just to make sure I didn't do anything silly. So for x is bigger than 5, we'll just do 5.01 equals, and we'll get something close to, but hopefully above that thing. Let me set it into a form where it should be equal to 0. So I'll do answer over 5. And then I'll add this across. So I'll do plus answer minus 6. And I should get something very slightly bigger than 0, which I do. Great. I feel good about that. Find an expression for the inverse. Right. What I'll do is I'll put a random x into the original. So I want to get my 0.68 back. So I'm going to do the root of 1 plus 2 answer. And I'm going to feed that thing into my inverse and just confirm I get my original back. And I do. So that is the inverse. And the domain is the range of the original, which is bigger than 0. Great. Explain why that's a problem, because it's many to 1 when it should be 1 to 1. I feel good about that. This one I can check with my integral button. So the integral of x to the 5. And now I've worked on this with people with different calculators. Just be very aware of how your calculator handles this. I'm using this calculator because it's my favorite. But yes, that is a 6th. The left-hand side will therefore be 5/6. And there's a show that, and I did show that, so that's good. Determine the exact value of that thing. I mean, you know exactly what I'm going to do. 1 over root 2 plus 1. Because the beautiful thing about things like this is you can walk away like knowing with certainty you've got it correct. So like, why wouldn't you? And then plus 1 over 2 plus root 3, it equals 1, which is exactly what I found. Okay, so what I'm going to do here is I'm going to plug in. So I found the fact that c is equal to 1. Let me just plug that in again. I'm going to check that on an integral. So that is going to be x over x plus 1 squared. And I'm going to do that between c being 1. And that's 1 plus 4 gives me 5. And I'm going to do minus ln 3 plus a third, and I should get a clean 0. Great. So c does equal to 1. That is correct with certainty. 6. Let me plug my values back in and again get a clean 0, where these are in degrees, but my calculator is currently set up for radians. So I'll do inverse tan of 3 first of all. So that x value, let's plug that back in. So tan answer minus 3 over tan answer minus 2, not a clean 0. Because I said that. Okay, oops. All right, so inverse tan of 3, that was my bad. So tan answer minus 3 over tan answer minus 2 That does give me clean 0. Inverse tan 3 plus 180. Plug this in. Tan answer minus 3 over tan answer minus 2. Clean 0. 135. Let me plug that in. Tan answer minus 3 over tan answer. And yes, I'm doing it for every single one, even though you kind of know if you get one, you get them all. Like, I want to really make sure I've got them all. So 315. Tan answer minus 3 over tan answer minus 2. Clean 0. Good. Let me check these are all in the range. Yep, they're between 0 and 360. I've got 2 bits on tan. I would expect tan to have 2 solutions in that interval. I found 4 solutions. I feel good that this is correct. 7, I like the way I did that. I will show you other methods for doing this, though, because I've got loads of time. So here, what else I could have done is, let's say I'd done the other substitution. Well, first of all, let me make clear where I got all of these substitutions from. So for this first one, I did it from sine 2a equals 2 sine a cos a, where I substituted in that a is equal to 4 theta, which is where the 2 sine 4 theta cos 4 theta comes from. And cos 2a, I said, was 1 minus 2 sine squared of a, where again, a is equal to 4 theta. But I could also have said 2 cos squared a minus 1. Now, what would have happened if I'd done that? I would have come to 2 sine 4 theta, cos 4 theta, tan 4 theta. And this would have been plus 2 cos squared theta minus 1. Well, again, this would have become 2 sine 4 theta cos 4 theta into sine 4 theta over cos 4 theta into this exact same thing. The cos 4 thetas would cancel again. You would get to 2 sine squared 4 theta plus 2 cos squared 4 theta minus 1. And by factorizing out a 2, we have the sine squared plus cos squared bit, which is just equal to 1. So that would also have got you 1. So prove that. Yes, I did. Okay, so what I'm going to do here is substitute in a random value of x. So I'm going to do, and I'm going to say if that thing is equal to my r sine form, so 1.678. And let's make sure this is in radians. Okay, radian, nope. Try that again. Guys, I'm so good at pressing the buttons. so good at pressing the buttons. Random answer, cos thing plus root 3 times sine of thing minus 2 sine of thing plus pi over 6 should be a clean 0, and it is. So that is correct. Hence solve this equation. I'm just going to plug them back in. But I'm going to plug them into this full thing here. So if I start off with the pi over 6 that I found, then cos answer minus root 3 of 1 minus sine answer should be clean 0, and it is. Let's try it again for pi over 2. So pi over 2, and then we've got cos answer minus root 3 into 1 minus sine answer. Again, clean 0. So these two values are correct. And this is sine of single x, so I would expect that to have two solutions in pi and 2 pi radians. I found them both. I feel good. Okay, question 9. Plug it in. Change of sign in the interval. I feel good about that. I will just show you because I'm not sure I did this. I think I might have, but just in case. So that was answer to the 4 minus answer minus 1 over 3 answer minus 2 is minus 1. 2 equals answer to the 4 minus answer minus 1 over 3 answer minus 2 is that. Change of sign in interval, continuous in interval, therefore root in interval. 1.15, I like that. You plug that in, it's negative. Change of sign in that interval, therefore 1.2, I like that. Explain, ooh. I don't know why I always, someone says, I don't know why I always make, I know exactly who you are. I think I do. Yeah, I know who you are. I don't know why I always make so many stupid mistakes on these types of question, and my tutor is always saying how careless I am. Yeah, it's because I know who you are, and it's because you're not paying attention. Welcome to the stream. No, I'll tell you why. When we say careless, so execution errors are likely to creep in. Execution errors are likely to creep in when you think a step is easy. So as soon as, a lot of the times people get through the really challenging part really simply, but then you get to the simple part and it's like, oh, it's just this bit. And then that's the part where stuff sort of creeps in. When you're not paying attention, that's when stuff creeps in. Also, yeah, I know yep. The easy parts always get you. Your words, not mine. So here we've got C. This looks like there's a root in the interval because there's a change of sign in the interval, but in fact there's not, because we can see there's an asymptote in there. And the reason why we can see there's an asymptote in there, in fact, I'll be explicit about that because I haven't done that yet. So based on the form, we know exactly where the vertical asymptote is going to be. It's when we get a divide by 0 error. So the vertical asymptote is when x equal, and that's when the bottom is equal to 0. So when 3x minus 2 equals 0, so when x equals 2/3. And so because there's a vertical asymptote between 0 and 1, there's a vertical asymptote in the region, or in the interval. Just about fit that in. So because there's that vertical asymptote in that interval, it means that you get the sign change without it going through 0. It's just a discontinuity. 10, sketch the gradient function. 0, 0, 0, good place to start. Then it's positive, negative, positive, negative. And it looks like a cubic, which is the differential of a quartic, which is good. 11, show that. I showed that. B. I showed the iteration, the start value, and the solution. I'm just going to stick with it. If this isn't what they want, like realistically in the real thing, I might have written everything out, but like, let's see what I can get away with, which is so not the right attitude. But like, we'll see what they want for the syllabus in the mark scheme. Explain why that's not a starting value. For 1 mark, it's because the derivative is close to 0. Determine the exact coordinates of all stationary points. I like how I did that, I'm not going to lie. So here, stationary points are where dy d theta equals 0. Is there a sensible way to check this? I mean, I got loads of time on the clock if I wanted to check this. Well, let me check dy. In fact, let me. I can use my calculator here. So, because otherwise it would just be boring if I was just redoing it. Let me check to make sure these are actually the theta values of the turning points, right? So let me check the derivative of 2 cos x plus cos 2x at x equals 0. I get 0. Let me check it at x equals pi. I get 0. Let me check it at x equals 2 pi over 3. I get 0. Let me check it at 4 pi over 3. I get 0. Cool. These are valid theta values for which dy d theta equals 0, which means these are the theta values at the turning points. And I'm sure I plugged them in correctly. You watched me plug them in. Although, let's be real, I would be doing this in the real thing. So let's do it. So 0 sine 2 answer plus 2 is 2. 0 2 cos answer plus cos 2 answer is 3. Pi equals sine 2 answer plus 2 is 2. Pi equals 2 cos answer plus cos 2 answer is minus 1. 2 pi over 3. Sine 2 answer plus 2 would be that. 2 pi over 3. 2 cos answer minus cos 2 answer is that should have been a plus. No, all right. I mean, I've got the time, and I would in the real thing. I just want to demonstrate what I would do. If I'm not getting it, I'm just always going to check, just so I can, like, for peace of mind, know it's correct. So that's a plus. That's correct. Let me check the 4 pi over 3. Sine 2 answer plus 2. Yep. 4 pi over 3. 2 cos theta plus cos 2 theta is, yeah. Okay, so those are the coordinates. Write down the equation of the line of symmetry. It's x equals 2, the end. And then we're into the section B part. So here, substitute the appropriate values to get the y coordinate. Well, I substituted in the t values of the x coordinates, and I found y equals minus 3 as required. Here, I plugged in the values, and I got 7.5 as required. And it's so many show that's, and I did do the show that. And I did show that this is the mean. And I did show that. And I did show that. And then the final point really is this point, which is this point here, where a is equal to 6. So it's 6x squared. B is equal to minus 7. Good. So it's plus 1. Well, let me just finally, I suppose, do this part. So it's plus c minus a difference of 5 all over 4. Oh, it was a minus. You see, this is why we check our work. So that should have been minus 36.5. See, not today, Satan. This is why we check our work. Made a little sign error right at the end. I added instead of subtracting. So minus 36.5. Even if even if it's super easy, that's when little mistakes creep in. That's why it's always worth checking. Even if you're like, dude, I've got this, it was fine. Okay, I feel good about that. I'm willing to bank that. Let's mark it. Okay, so let me scroll right to the top and let's see if I caught all the little execution errors. So x is bigger than 5. X squared minus 1 over 2 for x is bigger than 0. It's a many-to-one where it should be a one-to-one. 5, 6 over a 6. Yep. 4, you get 1. Yep. 5, c equals 1. Yep. I'm curious how they did this at the end. Okay, so they just compared parts. Yes. Okay, good. I did that correct. 71.6, 251.6, 135, good. They converted into sine squared and canceled down. That's good. So r equals 2, alpha equals pi over 6. Brilliant. Pi over 6 into pi over 2. Change in sign. Any value in there, and I did give one. I did this, I got that. So it's 1.2, correct. There's a change in sign, but there's an asymptoted x equals 2/3, so it's discontinuous. Perfect. This cubic there. So you need the zeros. Yeah, need the general shape. So it doesn't matter where these turning points are in the gradient. Oh, that's interesting. So that's one thing I didn't consider. So here, the fact that the original was an even function, which means it had mirror symmetry about the y-axis, meant that its derivative was an odd function, which needed to be rotationally symmetric about the origin. So I kind of stumbled into that one, but I didn't do it intentionally. So yeah, okay. General shape. Yeah, okay. So I get that, but that was interesting to note that they really like that even in odd function business. So this, yep, rearrange as required. Okay, so yeah, kind of plugging it in. Okay, so that's how they wanted me to formulate that. They wanted me to just sort of plug in, and I got this correct. So it's just good to know that that's how they wanted it formulated. 11c, the gradient is close to 0. So the next iteration is a long way from the root. Invalid is you cannot divide by 0. I'm not sure I said enough to get there, actually. So the problem with it, because I said it was close to 0. Now, if it's close to 0, you're going to end up a long way from the root. And if it's equal to 0, then you get the divide 0 error. I didn't explicitly say that. So that's just good to know to get all the way over the line there. Here, 2, 3, 2 minus 1, 2 minus that thingy. Yeah, cool. X equals 2. Minus 3, 7.5. So you get the thing. 15b. Yep, so you rearrange and you get that. Cool. I didn't do it in terms of, I did it in T1 and T2, but that's fine. In my opinion, anyway. This just does what it does. This, I got it. And then this is, well done for catching that, correct. So if I got anything wrong there, it's just little bits in the wording that they wanted, maybe to do with that even in odd function business when you're taking the derivative, a little bit on the wording for the Newton-Raphson, why you can't do it close to a turning point, but that's really it. Now that section B of this paper 3 was so much fun. I'm curious to do more of those to see if they're like that, where it's lots of show that's. Because if it's lots of show that's, then at least you know with certainty whether you're right or wrong, which is a great comfort. I think a lot of it is like you watched me read the insert and break down what it was saying and how I pieced meaning from it. I think, what do I think? I think look at the way I kind of distilled it. Instead of getting lost in the detail, I was like, functionally, what am I looking at? They're taking tangents at points, and it's where they intersect, and the intersection point has the average of the x coordinates. And I did the same with the normals. Like, it was just sort of understanding the function of what's happening there. Not the function in terms of like, f of x, but just functionally, what is this math doing? This is tangent. This is tangent. That's point of intersection. That's average of the x's. Understand the purpose of these things, and I think that's how you know where to look to make meaning of it to get the answer out. I'm curious to do more of those, especially because we're so close to the end now. I think the OCRs are quick. Like the edXLs actually take me close to a full 2 hours, whereas these OCRs, the AQA was quick and not fun, whereas this is quick and fun. I think I might stick here for the last couple of weeks or so of exam season. Especially if the OCRB is so under-catered to, and if this comprehension paper seems to be the weird part, the part that's kind of like off syllabus. I think this is a good place to be. So I might stick here for just the rest of exam season until we get into ESAT season. But if you guys don't like the sound of that, you know where to go. You can find me in the Discord. You can put streaming suggestions so I can kind of cover stuff that's most helpful to you. In the meantime, have yourselves a glorious, warm bank holiday weekend. Keep working hard. We only got like 4 weeks left. What am I? Am I ill? Is that what that means? I don't understand. But in the meantime, keep working hard. Have yourselves a fun weekend, and I will see you on the other side. All right, see you next time, guys. Bye-bye.